I'm going to talk you through some demo that we have worked on today in class, or we've been working on recently. We're talking about conservation of energy, and we're looking at a whole lot of things going on here. So I'm just going to demonstrate for you the rubber poppers that we're doing in class. We've got little miniature little ones, and we've got larger ones. And essentially, we can take and kind of flip this in here, and then we let it kind of go back to its shape, and we hear it pop, and it pops up, and we see that as popping off the floor, right? So if I were to do it right here, just went on some. And we can see it pop up. So I'll let this one kind of leave the screen here. So it's going to go, and it just popped up. And then we have these little alien critters, and we can do this one. Let's see if we can hit the camera. And coming at you. So here's what we're doing. So let's look at this from a side profile. We have this popper here. I'm going to call this location X. And when I invert this, it simply has this elastic capacity, this elastic ability that wants to spring back into its original shape, its original form. We just call that elastic potential energy. And then it pops and it goes shooting, it goes flying up here, it accelerates up and slows down and stops at Y. We would call at location Y. It's all gravitational potential energy. And then it falls back down to the Earth, and it would be kinetic energy the instant before at location Z, the instant before hitting. So this popper kind of goes up and stops and then travels back down. And we've looked at this. We've called this an upward launch in past physics topics. So let's do the math here. Let's talk about it conceptually, and let's do the math. So a lot of this is about understanding just the dynamics of what's taking place in this problem here. So rubber popper. So if you're taking notes at home. So let's just say the rubber popper, right? I have different ones here. So I'm just going to throw a number out. Let's say it's 10 grams. I've got 3 different ones. This one's like 15, this one's like 5, and this one's like, I don't know, I think this one's like 12. So just roughly 10 grams. We'll just say a ballpark on average. And let's say we would say that 10 grams, we know that we would have to divide this by 1,000 to get this into kilograms. So it's measurement here, mass of 0.01 kilograms. And let's say this pops up to a height of 3 meters. So we have information here. So let's solve. Let's solve for the potential energy at location Y. That it's gravitational. I'll just call it PE, potential energy sub gravity, sub G, gravitational, simply because of its position here. It's going to be M times G times H. And I know its mass. We just determined it was 0.01 kilograms. It's on Earth, 10 meters per second squared. And the height that it traveled to, we're going to say, is 3 meters. Now, this would be data. This is the data we collected in class, that we calculated this. We did these numbers here today. So these are close. These will be close to what we got here from class today. So if I multiply this out, I can take 0.01 times 10 times 3, and I find out that the total amount of energy, the total amount of gravitational potential energy, is 0.3 joules. So here's what we can say. We can say this very confidently. We can say that the amount of energy at location X is 0.3 joules. We can say that, right, the elastic potential here that's going to launch this up is 0.3 joules. We can say that the gravitational potential energy here at Y is 0.3 joules. And we can say that just before the instant before it hits, the amount of kinetic energy here is 0.3 joules. So we know this because conservation of energy says that, well, at all locations, it's going to have the same amount of energy. And everywhere in between here, too. It may have different amounts of different forms of mechanical energy at different parts. So like halfway up here, on its way up, it's going to have 1/2 potential and 1/2 kinetic. And over here, on its flight down, it's also going to have 1/2 potential and 1/2 kinetic. So it can have different ratios and different fractions depending on how high it is off the ground, and simply its velocity that would be related to its kinetic energy as well. So here's what we're going to do, and here's what you need to make sure you understand how to solve. And this is going to, I want you to follow with me, because I'm going to ask you, well, what was the velocity that it was launched upwards with, and what's the velocity in which it landed, came down with? So essentially the velocity at X and the velocity at Z. Because you want to know at Y, its velocity was 0. It stops instantaneously here. We learned this when we studied free fall, upward launches, two-dimensional motion. We've studied this several times. So here's what I know. I know that the potential energy at Y, right, the PE at location Y, is going to equal to the kinetic energy at location Z. Right? The total energy at Y is equal to the location energy at Z. We've established it. We've even quantified it, 0.3 joules. So I can say that mass times gravity times height is going to equal 1/2 mv squared here. Well, you'll see here, if I look at this equation algebraically, both sides contain mass, so I can get rid of it. Mass doesn't even matter here. And I'm asking you to solve for velocity. So we're going to isolate v. So you'll notice here what I have left is g times h equals 1/2 v squared, right? We got rid of m. M is gone. Mass doesn't matter here. It was essentially in free fall, in flight here. So to get rid of 1/2 on this side, I have to multiply it times 2. So I get rid of this, I need to multiply this side times 2. And I have v squared here. So my v squared here, right here, I need to square root v squared. I'm going to square root 2gh. So you'll find that the velocity is going to equal the square root of 2 times g times h. So I can do the math here. You'll find that the velocity is going to be 2 times 10 meters per second squared times a height of 3 meters. And you'll find that the velocity here is 7.7 meters per second. That its velocity at the moment of instant of being launched was 7.7 meters per second traveling upwards, and it was negative 7.7 meters per second the instant before it landed. And you'll find that this type of these types of numbers, we're really just saying conservation of energy holds true. And you could actually go back and check your work. You can take P equals mgh. We know that's going to equal 0.3. You could also take solve and go back and check your work and solve that Ke, right? We know that kinetic energy equals 1/2 mv squared. The velocity we just said was 7.7 meters per second. And I could take 0.5 times the mass we said was 0.01 times 7.7 squared, and I get a value of, let me get the glare out of there, 0.296. Maybe I can turn the light off and that'll help. Kinda. 0.296. So we're pretty darn close. We're pretty darn close. So that's for the rubber popper. Hopefully that helps. You can always go back and rewatch this. Now I'm going to walk you through the Alka-Seltzer Rocket. And I can go, remember, you can always go back and rewind and replay this. So now we're going to do the Alka-Seltzer Rocket. That was kind of part 2, phase 2. So let's look here. So here I have a film canister. The only difference here is that the film canister location X is going to be potential energy, but in this case here, we're going to go ahead and say that it's chemical potential energy because there's a reaction taking place in here. The fizzing is the process of effervescence. And here, we're still back to potential energy, gravitational potential, and Z, we're still back at kinetic energy. So similar, but a little bit different. This is chemical potential. And let's say that this here, let's say that our film canister was not only 5 grams, but let's say it popped up to a height of 7 meters. And that's, right, the height of 7 meters. That goes pretty high, but that's what happens. Alka-Seltzer rockets do pretty cool things. So I'm going to ask you the same line of questioning. I want you to think of in terms of the total energy here. Well, how much energy is here? Well, what we have information to solve for is the potential energy, right? The gravitational potential energy is going to be m times g times h. So I know the mass is 0.005 kilograms, and this would have had to been given, or you would have had to mass it in the classroom. On Earth, 10 meters per second squared, and we said it traveled to a height of 7 meters. That's multiplied. I don't want you to think that that's 0.7. So 0.005 kilograms times 10 meters per second squared times 7 meters. And I get a value of, I get a precise value of 0.49 joules. But I'm going to call this 0.5 joules just for the sake of just kind of a nice smoother number. And we're pretty close. We're 0.01. We're 1/100th of a joule off. So we'll go with this value. So we would say that the amount of chemical potential energy at this point right here is 0.5 joules. Really, it's the amount of energy needed to push the lid off. But we're going to go with this. That the potential energy here is 0.5 joules of gravitational potential energy, and the amount of kinetic energy at this location is 0.5 joules of kinetic energy. It's energy because it's moving. So here's what we're going to do. So here's what I want to know. I want to know what is the velocity upon being launched upwards and its velocity upon landing. Right? Let's figure out this velocity. I know upwards is positive and downwards is negative, but let's solve this. So I can use my energy theorem that the potential energy is going to equal the kinetic energy. And therefore, m times g times h is going to equal 1/2 mv squared. And you'll find, wow, these are in free fall. Mass doesn't matter. We've learned this several times. And therefore, when I isolate v, I'm doing this again. I have g times h equals 1/2 of v squared. I'm going to isolate and solve for v. Multiply both sides times 2. 2 gets rid of my half. Now I have 2gh equals v squared. Square root of both sides. And you'll find that v equals the square root of 2gh. That's a 2. So now I can plug in my numbers and solve here. I know that the velocity is going to equal the square root of 2 times 10 meters per second squared times 7 meters. In this case here, I find that my velocity, I get the velocity of 11.8 meters per second. Positive on the way up, negative on the way down. And in both scenarios, both the rubber popper and the Alka-Seltzer Rocket, they're really just looking at a form of an upward launch. And I added a second dimension here, so really we could say it's kind of two-dimensional motion. But we're now applying the concept of conservation of energy. It's in different forms. And now we're doing physics to where we can actually use the amounts of energy in it to make sense of other moving parts to the problems we're doing here as well. You're the best, but you knew that.